Hello, everyone. My name is Leo. It's my great pleasure to introduce today's speaker, Mahdi Salehi. Mahdi Salehi is an assistant professor in the Aerospace Engineering Department of Sharif University of Technology in Iran. So before joining Sharif, he was postdoctoral fellow at the Center for Interactive Research on Sustainability at the University of British Columbia, UBC. He received his PhD in mechanical engineering from UBC and his bachelor and master's degree in aerospace engineering from Sharif as well. Mahdi's primary research interest is turbulent combustion modeling. He developed OpenFoam solvers for turbulent reacting flow simulation using FlameNet and CSE combustion model, which is named as conditional source transformation. So he teaches thermodynamics, combustion, numerical methods in aerospace in the environmental course at the undergrad level, and computational fluid dynamics, combustion, and viscous flow at graduate level. So today's topic for the OpenFoam and combustion simulation is simulation of turbulent premixed flames using conditional source and estimation in OpenFoam. So I will leave the floor to Mahdi for the introduction and for CSE. Thank you.
Okay. Hi, Leo, and hello, everyone. Thank you very much for organizing this really good seminar series, and thank you very much for inviting me. I'm going to talk about the conditional source time estimation model, and especially how we use that model to simulate turbulent premixed flames in RANS and LES, and how we implement that model in OpenFoam. So so the transport equations for a reactive species, chemical reactive species, is like this. We all know that. And when we want to solve this equation in CFD code in turbulent flow, we cannot simply use the mean or the filtered scalar field to get the mean products, and we need a closure model. So one of the models that is out there is the first order CMC hypothesis. So in the first order CMC hypothesis, we basically, instead of using the mean or the filtered scalar field in the chemistry equations, we basically use the conditional scalar field, and basically by conditioning the scalar field, we reduce the fluctuations around the mean, and then we get a sort of good closure depending on the condition. Sometimes we have to condition it in two different variables, which is DCMC, double conditional moment closure. And we use the same closure model in CSE as well. In CMC, so the difference between CMC and CSE, that's what I'm gonna first express, is that in CMC, we solve transport equation for the conditional scalars. So for example, QK is why the conditional mass fraction of one of the species, the transport equation looks kind of like this. And so instead of in CSE, instead of solving this transport equation, we directly solve transport equations for the unconditional scalars, like the filtered or the mean scalars, and then solve an inverse problem to get the conditional ones. A little bit of the history. This model was proposed by Bush and Steiner when Kendall Bush, my PhD supervisor, was doing his postdoc at Center for Turbulence Research at Stanford University. And he basically was trying to use CMC in LES in his postdoc work. As you know, many combustion models, many LES combustion models are extended from RANS. So for example, we had transported PDF model developed and tested in the RANS context and then extended to LES. We also had the same story with CMC and flamed models as well. But there are other models that were proposed directly for LES. For example, the thickened flame model for premixed combustion, for example. It was first proposed as an LES subgrid combustion model. The same thing happened with CSE. So CSE was first proposed as an LES, as a way to apply CMC, first order CMC hypothesis in LES. So I will first, before talking about the theory of CMC, I want to give you an example, an analogy of a dynamic subgrid scale model, the one that we perhaps all know or we can easily read about, which is the dynamic Smagorinsky model. How do we develop and apply this model in LES is that we first start with an identity, which is the Germano identity. So this is, we have a filtering operation and then a test filtering, which is the hat sign here. And then we start with Germano identity. This is the identity, you can easily prove it. The left-hand side is known. The right-hand side is modeled with a gradient type model. Here is the constant Smagorinsky. And then we assume that the constant C is homogeneous at the test filter level. And by homogeneous is a fancy word for constant. Okay, so we assume that this parameter is in fact constant. At the test filter level, we have 9 equations. This is a tensor. We have 9 equations, 1 unknown, and one approach to get the unknown from these 9 equations proposed by Lilly is to solve a least square problem. We have the same thing with CSE. We start with this identity. So basically, to get the filtered or mean quantity, any scalar, like temperature or a species mass fraction, you can integrate the conditional scalar with a PDF, the PDF of the conditioning variable. The conditioning variable in premixed combustion is often taken as a reaction progress variable. In non-premixed combustion, it is often the mixture fraction. And yeah, so this is an identity. You need a presumed PDF model. This is used in CMC, in flamelet models as well. And we also use that in CSE to get the conditional scalars from the unconditional ones. So this is the identity. We solve transport equations for the filtered quantities. And then we write this equation in an ensemble of points. So we basically solve transport equations on LES grid. So here on the right-hand side, you can see the LES grid, the small grid. And then we basically apply this equation on every single cell in an ensemble. Ensemble is just like a test filter. So you can see the ensemble here as well. Yeah, so we have the following integral equation. We assume that the conditional averages are constant in the ensemble. And then this is called the Fredholm integral equation of the first kind. This is a vector. This is a matrix. Sort of, if we discretize that, this is a vector on the right-hand side. The discrete form of the conditional scalars is also a vector, alpha j. And then if you integrate the PDF in every bin, you get this matrix. And depending on the number of LES cells that we have on an ensemble, we have basically a matrix, a least square problem. We basically have a least square problem to solve to get the conditional averages. So the unknown is the conditional averages here. So the CSE homogeneity assumption, the fact that we assume the conditional averages are constant in an ensemble is also commonly taken at other combustion models as well. For example, in the flamelet models, in premixed combustion, for example, you solve a one-dimensional freely propagating flame and then use that as the presumed conditional moments for the entire domain. So you can call it FBI, FGM, or simply call it a flamelet model. It has been widely used and developed. And you also, in CMC, we also often use a coarse grid for the conditioning, for solving the conditional transport equation for the conditional scalars. So the grid that we use for solving transport equation with conditional scalars is often larger than the LAS grid, and they do that to reduce the computational cost. So I'm only citing one paper by Salvador, but there are other publications as well. All right, so if you directly solve this least square problem, basically minimize the residual in these n equations, m unknowns, then you get these blue lines. Because this problem, the Fredholm integral equation of the first kind, is ill-posed. So we need to regularize that. So in this figure, you see the water vapor conditioned on a reaction progress variable in a premixed flame, in a Bunsen flame. I got this from an CSC LES of this turbulent Bunsen flame. And the true conditional averages should look like the dashed line. But if you don't regularize the problem, if you directly only minimize the residual in your, n equations, m unknowns, then you get these blue lines, which is obviously wrong because it's not regularized. One way to regularize this problem, this inverse problem, is the Tikhonov approach. In the Tikhonov approach, you not only minimize the residual, which is p times alpha equals phi, but you also minimize the difference between the solution and an a priori knowledge of the solution. This is done by a regularization parameter, and then the regularization parameter can be obtained from a simple algebraic equation. You can see this this is the trace of this transpose of this matrix times its, and then M is the size of the matrix. Or you can use a more fancy approach like the L-curve approach. So the idea of L-curve is that if I don't, if my regularization parameter is 0, I only minimize the residual in p times alpha equals phi, then I get the blue lines. And then the residual in the solution, the blue line, is really high. So you start from somewhere up here. And then as you increase the regularization parameter, then you also minimize the difference between the solution and an a priori knowledge of the solution. But as much as you don't increase the residual, so the solution is somewhere at the corner, you get a lambda, and then you can put that here to get the solution. The a priori knowledge of the solution can be a flamelet solution, could be the solution from the previous time step. Get something that is similar to your final solution. So in this table, you can see the history of CSE was proposed by Bush and Steiner in an a priori analysis using DNS data. And then they also applied that in an LAS code to simulate the Sandia flame cases. And then Huang and Bush used a RANS code to simulate an igniting jet flame with natural gas, and then they used TGLDM chemistry. I will talk about the TGLDM chemistry in a few slides. And then Huang and Bush used that in LES with flamelet chemistry, use CSE with flamelet chemistry. I will also talk about flamelets, how we can use CSE with flamelet chemistry. And then there are also a few other publications related, all in non-premixed flames. Then Jinbei used DNS data to show that CSE also works in premixed combustion. There are also some other publications on different non-premixed combustion as well. Myself, in my PhD work, applied this premixed version of CSE first in a RANS code to simulate the benzene flame, again with TGLM chemistry. And then I also collaborated with Daniela Dovizio, a PhD student working with Cecil Laveau to simulate a bluff body flame, again in RANS. And Girish Nevarti also used CS in premixed combustion to simulate an IC engine with natural gas in TGLDN. Nassim Shahbazian and I also applied CSC in LES of a benzene flame. And then it was also used in other combustion regimes like mild combustion and partially premixed stratified flame, mainly in Cecil Lovo's group at Waterloo. And for that, for those flames, they had to try double conditioning CSC. I won't talk about DCSC, double conditioning CSC. Yeah, and then there are recent publications on real fuels, like these last few publications on a spray combustion as well. Leo, oh, this is Leo's paper, LES of spray A. And there are also some recent publications as well that I didn't include in this paper. For full citations on like where these papers are published, you can refer to my recent paper in Combustion of Flame. So as you saw, many of these models use flamelet chemistry, to use TGLDM chemistry. And in TGLDM, we basically first look at obtain the boundaries of a hyperdimensional composition space with a simple element balance. So you have a mixture, you do an element balance, and you find the boundaries of the composition space in the hyperdimensional subspace. And then you start from the boundaries with a canonical flame, like an igniting flame or a premixed freely propagating flame, to solve a trajectory all the way to equilibrium. So this is how it looks, for example, so these are different trajectories starting from the boundaries of the hyperdimensional space, and it goes all the way to the equilibrium, and it's colored by the source term of the CO2 mass fraction production term. And then it's parameter. And then finally, once we have all these data, we put it on a lower dimensional subspace. Here, it is a two-dimensional space, which is a function of water and CO2 mass fraction. So this paper, when basically Huang and Bush wrote the paper on TGLDM, submitted it, then one of the reviews was that this was already done by Pope and Moss, but was not published in peer review. So yeah, so it's basically an internal report at Cornell University. So if you want to cite TGLDM, you should cite this first publication. All right, so we also, before going to implementation of this model in OpenFoam, I also need to talk about the PPDF model, the presumed PDF models that we use in premixed combustion. We often use the beta PDF. It's a good candidate unless you do RANS simulation of a flame in the flamelet regime. If you do LES under certain conditions, it's okay to use the beta PDF. And also for high Karlovitz number premix flames, you can also use the beta PDF as well. There are other options available. For example, here, the solid line is basically the experimental PDF. It's obtained from the Cambridge Sandia flame, the Mark Sweeney burner. And the beta PDF is the dashed dot blue line. As you can see, it doesn't really match the the solid line, the experimental PDF. But other models, here we use the modified laminar flamelet PDF model. You can see the details in this publication of this model. So here I brought some results. This is the RANS simulation of a Bunsen flame. So this is a Bunsen flame. This is the Chenadol burner. And at 4 different axial locations, you can see the profiles of the CO mass fractions in 3 different flames, F1, F2, and F3. And the dashed line is the results of using the beta PDF, and the solid line is the results of using a flamelet PDF, a modified laminar flamelet PDF. And as you can see, obviously, the beta PDF is not really doing a good job. This is a RANS simulation. For the same, just flame F3. So for flame F3, we also tried LES of this flame. And this is all done with flamelet chemistry, not with CSE, because this flame is actually in the flamelet regime. And then you don't see that much difference between the beta PDF and the new PDF, the flamelet PDF. So in LES, then we basically did an analysis. The same analysis was done by Benoit Fiorina. And you basically look at a one-dimensional freely propagating flame, you filter it at different filter sizes, and you calculate the filtered flame speed, and as a function of different filter sizes relative to the laminar flame thickness, you calculate the filtered flame speed relative to the laminar flame speed. And for large filters, beta PDF doesn't really do a really good job. But for the small filter sizes, it's kind of okay. So here, the reason that the beta PDF and the flamelet PDF are very similar is that the filter size was on the order of the laminar flame thickness. So if you are in that condition, you're good to go with the beta PDF. There are other options available. For example, Nielsen et al. Proposed a correlation that if you use the beta PDF for large filter sizes, then you can use that correlation to correct your solution. Ken Bray and also Lukovic in his group, as well as Michael Fetzner, also proposed a few models based on the Bray's idea of using the flamelet PDF. You can follow the publications. I don't talk too much about the details, but it's basically a bimodal PDF, one delta function in reactants, one in products, and an interior distribution that comes from a flamelet solution. So they're all talking about pretty much the same functional forms. And then you can also, recently I've seen people use machine learning approaches to get a presumed PDF. You can also do that as well. But then that's how, in this diagram, you can see how the CSE model works. We have OpenFoam. We solve transport equations for the scalars that we need in our chemistry model. We solve transport equations for the scalars that we need to construct the PDF. Here is the mean and the variance of the reaction progress variable. And then we have the PDF. For example, we also have the water mass fraction here. We put them in the CSE. We solve the CSE inverse problem to get that conditional water mass fraction. Here, because we use the CO2, normalized CO2 mass fraction for the reaction progress variable, then we can also readily get this with a linear function. And then we put that in the TGLEM table, get the conditional reaction rates. We use the PDF to get the unconditional reaction rates back in OpenFoam for the source terms of these different species. So how do we implement that in OpenFoam? So basically OpenFoam, you get the mesh. In your code, it's just one line, create mesh. And then you basically use inheritance. Your mesh is an object. And then you use inheritance to get the fields from the mesh. And why it's called OpenFoam. Open field, it's an open source field operations and manipulation. So the fields are object-oriented programming we use in OpenFoam. The fields are object based on the mesh, and then all the operators are either defined or overloaded to basically enable us to write a simple transport equation just like this in a very simple way so that we can easily put them together and solve our equations. The really extra thing that we need to do in CSE is to construct the ensembles. For that, OpenFoam has something called cell set dig, and you can use that to basically decompose your domain into different domains. You can use a box, for example. You can use different geometry types to get different ensembles, and then in your code, you can have access to those ensembles, those parts of your mesh. And then this is just basically a list of what we have in OpenFoam, in our OpenFoam solver. We use reacting foam. We developed that to reacting CSE, TGLE, and foam. I use Tikhonov approach here. And then P equation, you need that. You have that in reacting foam. We have 3 different classes, one for PDF, one for the ILDM is basically a general way, and you can reuse TGLDM as an ILDM sort of type class for loading the chemistry. We use non-negative least square solvers to solve the CSE inverse problem. And then we also solve transport equations for variance of the progress variable for the CTIL, which is the progress variable, to make the PDF. And then yeah, we have transport equations for the scalars. We have also transport equation for sigma, a quantity that we use to write a model for the condition for the scalar dissipation rate, which is a sinc term in the variance transport equation. And then all the CSE inverse problems are done in one specific type of a part of the code, and then they include that in the solver based on the diagram that I showed you. So the first test case that I will show you is the Bunsen burner of the Chanadol, and it's basically a stoichiometric methane air mixture that enters through this pipe surrounded by hot pilot products. We perform both Rance and Elias of this flame, and in Elias, the inflow is taken from a precursor periodic pipe simulation. And then once we did that in LES, we basically got these solutions for the conditional scale. So this is the conditional scale of water condition on the reaction progress variable. And the symbols are the solutions of a freely propagating laminar premixed flames. And as you can see, once we solve the CSE inverse problem, we pretty much get the same thing. And the reason is that this flame is mainly in the flamelet regime. So I don't want to talk about like really whether we have flamelet regimes or not in premixed combustion. There are tons of publications on that. I'm not going to talk about that. But then I strongly encourage you to put your simulation data in this sort of regime diagram proposed by Heinz Pitch. And you basically, based on this, the terminologies in this regime diagram, we have a resolved flame surface, we have corrugated flamelets, we have thin reaction zones, we have broken reaction zones. And then you can see that the flame F3 in the Chanadol burner, Bunsen burner, is basically mainly in the flamelet regime. Okay, so we tried a different flame at with higher turbulence intensity. This was Omer Golder's burner. It is again a Bunsen burner. So the burner tip here is compared to the channel level burner. So in the channel level, you have a central pipe surrounded by pilots, hot pilot products. And then here, the pilot is very small, very small. But then the main difference is that they have a metal mesh screen here. It's a grid to generate turbulence, okay? So the velocity is kind of smaller compared to channel level burner, but because of this grid, it generates a lot of turbulence, and the flame is in the twin reaction zone regime. So this is the isosurface of C tilde, the progress variable equals to 0.5. These are the temperature contours. And then once we got the results and put the solution in this regime diagram, we can clearly see that the flame is in the mainly in the twin reaction zone regime, some part in the regime. And then once we solved the CSE inverse problem based on the unconditional ones, again, the symbols are the one unstringed laminar premixed flame. And then as you can see, near the burner tip, I will go back. So here's, near the burner tip, it's pretty much deviated to a great extent from the unstringed laminar premixed flame. And then as we increase, as we go above the burner, as we increase the axial location, then we sort of fall into the flamelet regime. And this is basically because of the nature of this, the turbulence in this flame. So it's grid generated turbulence. It decays exponentially. So near the inlet, just at the burner tip, you have a lot of turbulence. And then the flame is very stretched and strained. So it is sort of deviated from the unstrained solution. But then the turbulence intensity decreases, and then you basically get the flame solution. At that time, because in this burner, these conditional averages are not measured. So at that time, in order to sort of compare and show that, you know, our results are okay, we used a counterflow laminar premixed flame. So you have premixed gases coming from this side, you have hot pilot products at the same equivalence ratio coming from the above, and then you have the flame zone here. And then as you increase the velocity, the flame is stretched. And then as you can see, we realize that, you know, it's very simple. You can use Cantera to use this, to do these calculations. And if you put it in this context, which is relevant to CSE, you can see that basically by increasing the strain, the conditional averages tend to, of the mass fraction of the profiles of mass fraction of water versus mass fraction of CO2 tends to a straight line, just like what we got with CSE. But then later on, we got our hands on Sosong Bai's DNS data at Lund University. I guess that's the only DNS data, turbulent reacting flow DNS data that is available to everyone to download and use it. So then for this flame, it comes at 3 different conditions, 4 different conditions, 4 different Carnot numbers, 6, 74, 540, and 4,100. So for that, we also calculated the conditional averages of water condition on the reaction progress variable, which is CO2 normalized. And then the blue line here is the unstrained laminar premixed flame. And then the black line is the actual conditional averages that we get from DNS. So I got this figure right yesterday from these publications. So other lines like the red line and the blue lines, there are different models. I won't talk about them right now. But then basically by analyzing this DNS data, we realized that what we get with CSE was pretty much sort of correct. I also have one slide from Grish Nevarty's simulation of an internal combustion engine. So this is the mean progress variable, and they use CSE to calculate this is RANS, CSE RANS, to basically calculate the dry NOx at the outlet of the engine, and then they compare that with the experimental data. Finally, so I will also want to talk about some recent works that we have done to improve the performance of the CSE. And it's basically CSE with, we tried a sort of more optimized regularization parameter. So these are Bernstein basis polynomials. This is the Bernstein, this is the equation of the Bernstein basis polynomials. They have interesting properties. They form a partition of unity. So if at every location, if you sum them up, it equals to 1. And so when I started to work at Sharif University of Technology, you know, as an assistant professor, you're supposed to do some administrative works. And then I was forced to organize a poster series for graduate students. And yeah, so since I organized that, I kind of like, okay, now let's look at the posters. And then I saw these Bernstein basis polynomials in one of the posters. It was doing something relative to computer graphics. And I was like, these are insanely similar to the conditional scalars in a turbulent reacting flow, for example, in a premixed combustion. So the solid line is very similar to a reactant species. The dashed block line is very similar to a product species. And then the other lines are very similar to the minors that form throughout the combustion process. So I was like, this could be an excellent regularization, reduced order model, and we should be able to use that. So I had this really smart student, Amir. He's currently working with Cecile DeVoe at Waterloo. And then we basically use these Bernstein basis polynomials as a reduced order model for the conditional scalars. So for the conditional scalars, we write them as a series expansion of Bernstein basis polynomials. And then they are really good reduced order models. So for example, I got these data. These are the conditional water, CO2, methane, O2, hydrogen, and CO mass fractions conditioned on temperature. I guess the conditioning variable was temperature of the Cambridge Sandia flame, the Mark Sweeney burner. And then we fitted Bernstein basis polynomials. So the squares are the experimentally measured conditional scalars. And then the blue line is the Bernstein fit. We just fit a Bernstein basis polynomial to them. And then we calculated the relative error between the experimental data and the Bernstein fit. As you can see, as we increase the number of Bernstein basis polynomials above 3, so for only 3 Bernstein basis, which is 4, because n starts with 0, 1, 2, 3, 4. With 4 Bernstein basis polynomials, the errors in major species are all less than 1%. Okay, so instead of solving in CSE for the conditioning scalars, the discretized conditioning scalars, which is like 50 unknowns, 20 unknowns, 50 unknowns, what we do is that we solve for the Bernstein constants. So we basically put this equation. I'll go back one slide. So this is our model for the conditional scalars. So we basically put this equation into the CSE inverse problem, this integral equation. We assume that the conditional scalars are constant in the ensemble. Therefore, these constants, which are unknown, comes out, And then I have this, again, linear system of equations. But then instead of solving for 50 unknowns, I solve for 4 unknowns, 5 unknowns. We did some a priori analysis using DNS data, system bias data. Thank you very much for sharing this data with the whole community at large. And then we basically, so this is, for example, the CO2 mass fraction production rate, CO2 production rate in DNS. This is the filtered and coarsened DNS. And this is what we get with BD-CSC, we call it, CSC with Bernstein decomposition. So they're pretty much similar. And you can also see all the points. This is just one slide through the three-dimensional DNS data. You can see all the results here. And here, the vertical axis is the predictions using the CSC with Bernstein decomposition. And then the vertical axis is CSE, is the actual DNS for the filtered CO2 production rate. And they match pretty well. And yeah, so here, again, for CO2 production rate, we calculated the relative error as a function of the number of LES cells in an ensemble. So as sort of some size of the ensemble. As n increases, the size of the ensemble, the test filter in LES, you can say, increases. As n decreases, the ensemble becomes smaller and smaller. The green line is the conventional CSC approach. So as you can see, for example, in this case, which is highly turbulent, if you want to get the 50 unknowns in the conventional CSE, which is the discrete form of the conditioning the conditional averages, you need to have at least 1,000 to roughly around 400, 500 LES cells in your ensemble. But with the BDCSE, because you're solving for like a few unknowns, we have a really good reduced order models for the conditional scalars. Then you can also have very small ensembles, like 32, 16 ensembles with 32 to 16 points. And that's why we call it some sort of localized CSE approach. And then the other lines, so the orange line is the BDCSE. The other lines, for example, the purple line here is basically the average in the course grid. So you look at the ensemble, and then this is your course grid. You average that and calculate the error compared to the DNS data. And then the red line, the green line is the CMC, the course grid CMC, where you basically average the scalars and use the first order CMC hypothesis to get the mean, the conditionally average CO2 production rates. And this basically shows that the first order CMC hypothesis is also pretty good. Finally, I want to talk about how we can use CSE with flamelet chemistry. So this approach is, we sometimes call it laminar flamelet decomposition. So similar to the one I just described, we basically approximate the conditional scalars as a series expansions of flamelets. For example, in a premixed combustion, we can use a strain flamelets. So we use it in a reactant product counterflow configuration and get like 10, 20 flamelets. And then we write the conditional averages as a series expansions of these flamelets with the contribution of different flamelets being the unknown. And then we solve the CSE inverse problem for these unknowns. So we basically put this equation into the CSE inverse problem, CSE integral equation. And then we assume that the conditional averages are homogeneous at the LFD ensemble level. then the ANs are unknowns and constant. We get them out of the integral, solve the integral for each flamelet, and get this left-hand side matrix, and we also get the right-hand side matrix vector from solving transport equations for a second species. So for example, you solve one transport equation for CO2 and you solve another transport equations for H2O, for water, to get this inverse problem and get the right-hand side of this inverse problem. And then again, for the biased DNS data, this is just a priori analysis. I have my PhD student currently trying to put this in Alias in OpenFoam, and then another PhD student trying to put the BDCSE for premixed combustion in OpenFoam as well. So these are just a priori analysis, and as you can see, it is way better than just using an unstrained flamelet, especially when your Carlowitz number is really high. So if your Carlowitz number is high, and then you use an unstrained flamelet, this is just what you have in commercial CFD softwares, like in Fluent and Star System Plus. And if you simulate a highly turbulent premix flame, because you're overestimating this reaction source term, the chemical reaction source terms, then the flame is going to be much shorter compared to what it has to be in reality. For lower turbulent conditions, it's okay. You can get the unstrained flamelet, just the models that you have in commercial softwares. But one way to get the strained flamelet library coupled with your OpenFoam solvers is to basically go for LFD, laminar flamelet decomposition approach. Yes, so I'm pretty much done. Thank you very much for listening to my talk. If you have any questions, please let me know. I am available to collaborate. This is my email address. If you want to work on CSE, please let me know. We can certainly collaborate.
Thank you very much, Mahdi. We do have a couple questions from the audience. Apologize first if I pronounce your name wrong. First, we have a question from Ishan. One of the things is that in most CMC applications, the conditional fluctuations around the conditional mean are neglected in the large CMC cells. So this has shown to be inaccurate in flames having large local extinction, for example, Sandia flame F, when there's a very high Reynolds number. So how does the CSE cater to these complex flames?
Well, if you have local extinction, if you have multi-regime combustion, then you have to go for double conditioning CMC. So the first order CMC hypothesis, this equation is not accurate enough. If you use two conditioning variables, for example, in Sandia flame F, if you use both mixture fraction and reaction progress variable as the conditioning variables in DCMC or DCSE, then we should be able to use the CMC hypothesis as well. Then you also need the joint PDF, which is a big challenge.
Yeah, thank you. We also have a question from Pranay. The question, we actually had two, so I will start with the first question first, and then could you explain what exactly is a conditional scalar? I mean, physical significance of it, which I assume it was about premixed flame for your case. And so his question was, it seems that this concept is borrowed from mathematics, conditional probability. So he just wanted you to ask, explain what's the physical significance of this. Yeah.
Okay, so I can use this picture. So, for example, if this is your condition, your computational domain, then if you do DNS in each LES cell, which is one of these cells, you have, for example, 1,000, 2,000 DNS cells. So if you just average them, average the CO2 mass fraction, for example, add them up, divide by the numbers, this is unconditional average. But if you look at some sort of conditioning variable, for example, temperature, if you look at their temperature and then put them in different bins, okay, and then average in each bin, then that's a conditional scalar. So for example, you look at all these like 2000, 3000 cells, and then, okay, I want to calculate the CO2 condition on temperature, for example, or temperature condition on CO2, it doesn't matter. Then you look at their temperature values, you have like 50 bins, 10 bins, 20 bins in the temperature, and then you put different cells in each bins based on their temperature, and then average that together. That's some sort of the physical significance of the conditional averaging. And the second question was the same?
The second question is more about what is the limitation of CSE or CMC model in solving combustion problems? Yeah, if you can see.
Okay, so yeah, so in order the limitations, the first order, the CMC hypothesis, the first order CMC hypothesis is accurate enough. But if you basically have, for example, as I said, local extinction in the first question, then as far as you increase the conditioning variables, you're good to go. But then if you increase the conditioning variables, then you also need, just like flamelet models, like multidimensional flamelets or CMC, you need the joint PDF. Okay, so one of the limitations of these types of models is to get the PDF, because we model the PDF. We need a model for the PDF. We don't solve transport equations for the PDF. So one of the limitations is the PDF. You need to, and especially in CSE, because the PDF is the kernel of your inversion. And then it's much more important to have a good PDF in CSE compared to CMC. CMC has other challenges as well, like, for example, the conditional scalar dissipation rates. That's one of the challenges. And then the other limitations is basically in CSE, you need to have ensembles. So for example, if you want to look at an igniting premixed flame, at time equals 0, you only have one cell which is igniting. So I don't really know how we can solve that with CSE. We always apply CSE. I mean, I personally always applied CSE on top of flamelet model. So for example, for a Bunsen burner, I solve it with flamelets. So I presume the conditional averages. And then I switch to CSE, which is basically solving this inverse problem to get the conditional average.
I think that's everything from the audience. I have 1 or 2 questions if you still have a couple of minutes. All the premix flames you explained, I assume the progress variable is the TGLDM is constructed with CO2 and H2O.
Yes.
So what if you have a flame that has 2-stage behavior? How would CO2 and H2O capture 2-stage?
What do you mean by the 2-stage behavior?
2-stage combustion. So let's say if you have NTC behavior or N-heptane or endodecane, how would TGLDM work?
Well, you mean you first have a pyrolysis kind of phase, and then you have the combustion. Well, we tried with a master's student, a complex fuel, and the trajectories were like, going all over the place. If you increase the dimensions, perhaps. I never tried that. So I always work with simple fuels like methane. But if you increase the transport the dimensions, I have a master's students currently working on that. And maybe use some sort of advanced interpolation kind of schemes like the machine learning type schemes. Then we might be able to get that. But we have to try it. I don't know. I never tried that.
Yeah. I think Professor John has question himself.
Yes, thank you very much for your talk. So just now you mentioned the DCSE, right? Yes. So have you compared the results using CSE and DCSE for capturing some like a local extinction or blow off and so on?
Well, I know Cecile DeVoe at Waterloo is currently trying that.
Okay.
With my former master's student, she's currently her PhD student. He's trying to simulate Sandia Flame F with that. But I won't be surprised if it is that much different from the currently published results in CMC. So you get error if you use one conditioning CMC, but if you use two conditioning, the results are going to be improved definitely.
Okay, thank you very much. So how about in DCSE, how about the cost, the computational cost? Because for DCMC, actually, the implementation is very complicated, and the cost actually is. But you use they use a cost mesh, okay? So reduce some computational cost. I'm not sure for the DCSE, what is the cost for that?
Yeah, so Jeff Laban did, so he basically got a CMC code from this guy at Belgium, I forgot his name, and then put CSE in the same code. And his conclusion was that CSE, the computational cost of DCS, it was actually DCMC and DCSE. If I'm not wrong, maybe single condition. I'm not sure. But then he showed that CSE, the computational cost of CSE is lower compared to CMC. With this new approach that we recently proposed, this reduced order model based on the Bernstein polynomials, you can also use that in CMC as well. It's extremely reduced. I mean, we did some RANS calculations with both BD CSE, CSE with Bernstein decomposition, and then with CSE, the regular CSE as well. And the computational cost was reduced by 30%, I guess.
Okay.
Just the Jeff's paper was single conditioning, I think. So it was direct comparison with CMC.
Okay.
Yeah. We also have one more question from Professor Wang.
Hello, Mahdi. It's a great talk, and I have two comments on the CMC and the CSE. The first thing is the first order assumption. We all know that, but for CMC there is issue is with someone like Andreas Kronberg also tried to implement the second order CMC model, and it's very complicated, and to mainly want to include the fluctuations around the conditional mean. But I found if you use the CSE, maybe it's a bit easier because it's easier to solve the second order of the scalar transport equations. Is that?
Okay, so by second order you mean like the variance, the variance. Okay, so nobody tried it before. In the appendix on my thesis, I touched on that a little bit, and I propose to use some sort of Bayesian approach, because if you use Bayesian approach, you also get some sort of conditional fluctuations as well. But we never tried that. So no formulation is out there, and it's something perhaps to work on. I can think on the fly that maybe you need to solve transport equation for the variance as well, and then use the inverse problem in a similar way to get the second order conditioning scalars. But with double conditioning, I mean, that's Kendall's PhD work was second order CMC. And then at the end of the day, they realized that maybe double conditioning is a better candidate compared to the second order CMC.
Okay. And the second thing is, could you please give more explanation about the inverse process? I found it's helpful. I know CSE, but I never digged a lot to see what happened there until you showed that there is the inverse process there. Because you know, in the CMC equations, people usually made assumptions to neglect the residue terms, several residue terms, and it may lead to error, especially in low Reynolds numbers or various or in a flame with different region with various Reynolds numbers. And so if we don't solve the conditional mean equations, we only solve the transport equations, this is no problem. But I think there may be errors in the inverse process. Could you explain that?
Well, yeah, so this is basically in CSE compared to CMC. In CMC, we basically use basic principles to get transport equations and get the conditional transport equations. But in CSE, is just based on some sort of scale similarity hypothesis. Just it's an alias type approach, and this is a necessary condition to get conditional scalars. We assume that this is also a sufficient condition. And then we also assume that the conditional averages are homogeneous at the test filter level. And then the rest is just discretizing and solving an inverse problem. Oops, it's ill-posed. We have to regularize it. So the whole process of getting the inverse problem is not that much difficult. The only assumption is that this condition is not only necessary, but also sufficient to get the conditional scalars. For that, we always relied on numerical experiments. So we used DNS data and it worked. We put it in alias codes and then it also worked. So yeah, so it has been working so far for different flames at different conditions, at different regimes. And we are trying and continuing to basically try different conditions and see how the model works in different conditions. So I cannot answer like mathematically that, you know, with this, therefore it should work. It's been working.
What I mean is, could you explain more how the inverse process works? Maybe I didn't follow well here.
Okay, so this is, as I said, a necessary condition to give the conditional scalars. We assume that this is constant in an ensemble. We write this equation, okay, for each LES cell in the ensemble. So the ensemble is like the purple cubes, and then the LES cells are these smaller cubes. And then for this, we write these equations for every cell. So for example, if you have 20 cells, you have 20 equations. If you assume that this vector is constant, is the same for all those cells, then you have basically this is just the unknown, and then you solve for that unknown. In practice, so just to write that mathematically, we write this for every cell, and then here Ri is the, you know, coordinate of that cell. So we basically have a vector here, and then a matrix here. So this is basically the PDF at every location, at every LES cell. This is your vector, this is a matrix. You assume that this is constant at the ensemble level for all the cells. LES cells, you have the same conditional average, just like CMC supergrid, and then you solve for this vector.
Mhm. Okay. Okay. Okay.
I think,
Thank you.
thank you. Thank you, Mahdi. I don't think we have any other questions, unless I'm wrong. Thank you very much for giving us the talk. And we do have one more CSE coming up very soon, I guess, from Cecile. It will be next week or the week after. Yeah, so there'll be doubly conditioning CSE, I think. So we will have more CSE
Great.
talks. Thanks again, and thank you everyone for joining this webinar. And
Okay, thank you very much, Mahdi.
Thanks.
Okay, thank you. See you. Bye-bye. Thank you, Leo.
Thank you all. Thank you for inviting me. Bye.
Bye-bye. Have a nice weekend. Bye-bye.